Okay, cool. All right, so you should all still be able to see my screen. Let me double check. Yep. All right, so energy, first law of thermodynamics, energy, right? So we learned about oxidation reduction already, but this reaction, along with really any reaction we deal with in this class, has energy involved, but we don't write it in the equation, or we haven't so far. And sometimes you don't write it in the equation. You could just say it's endothermic, exothermic, whatever the case may be. But here's an example of hand warmers, right? So hand warmers, you know, you crunch them up and you can put them in your glove or whatever, and they warm your hand slowly over maybe an hour or two, right? And the reason why is a slow oxidation process of little pieces of iron in there when they come in contact with the oxygen. So, and that releases heat. And the heat being released means you can feel it. So we're going to get a good idea of how energy is transferred today. So we'll talk about ice cubes, stuff like that, and the way heat is transferred. So if it's an exothermic reaction, that means if you touch it, it should be hot. So exothermic, you should be getting heat from something. So hand warmers are a great example. Yeah, there's a bunch of things. Fire is exothermic, right? It releases heat. So then it's endothermic. So exothermic would be releases heat. Then there is endothermic. These are very important definitions. And then it makes sense. Exo, exit, release. Endo, take in. So endothermic means that you gains heat. So it has heat go into the system. So what that means is an ice cube. An ice cube is endothermic, meaning in that process, it's going to be releasing coldness. In other words, gaining heat. There's no such thing as cold. That's a weird concept to understand, but cold doesn't exist. The thing that makes things cold is the absence of heat, the absence of thermal energy. So if we understand that and understand that cold doesn't exist, and that when you put an ice cube into water, the heat from the water actually warms up the ice cube. So the heat from the water is being exothermic, and the ice cube is being endothermic by gaining that heat. Once it gains that heat, it ends up changing state and it melts. So yeah, that's a good concept to understand. So also with energy, we have this thing called work. So we know energy, by definition, is the capacity to do work. And what we mean by work is we mean the physics definition of work, not just, yo, I'm gonna do work, bro, go to the gym. But I mean, going to the gym does this work also, chemical work. But how's the chat? Let's see. Oh, you did not hear me. Oh no. Does everyone else hear me? Hold on.
Okay. I can hear you.
Okay, yeah. Is it good or is it low? I just moved the mic closer to my face. Okay. Okay, so Marie Madeline, maybe it's the sound on your speaker or something. I'm not sure. So maybe you could fix that. But okay. So work in a physics point of view is the force acting over a distance. So if you push something, that's doing work because you're applying a force to it over a certain distance. Now, and then that leads to an equation, right? This equation is important. So it's a physics equation. So if you took physics before, this should be familiar, but work equals force times distance. So the force is usually in newtons, and distance is usually meters, but it really doesn't matter. The unit changes a lot. But just know right now that it's a force acting over a distance. And then energy and work could be done. Well, energy can be done on something, but work can be done on something. Energy can be transferred between things. So if I push something, I'm doing work on the object and I'm transferring my energy to the work. So the energy that's in my body, that's in my calories, that's from my calories, from my metabolism, is being moved to my muscles. My muscles are contracting and I'm pushing something to do work. So the energy is being transferred from chemical bonds in my body to physical work. So that's one example of how energy can be transferred. And it doesn't just disappear. It goes into the object. It goes into moving molecules around me also. And then that energy dissipates, or that energy moves molecules all the time. So also energy can be exchanged through collisions, which we've seen in chemical reactions. We talked about very briefly radioactivity, where you have a buildup of energy inside the nucleus of the protons coming in close contact, which creates a burst of the nucleus. That is an example of collisions gaining energy, and then boom. So there's two types of energy. The first one's kinetic. The second one is potential. So kinetic energy is energy of motion. We did cover this already. Just know that it's energy of motion. We're not going to go over 1/2 mv squared. That's more physics. And then you have thermal energy. So thermal energy is basically a type of kinetic energy that is with respect to the temperature of the molecules. So a higher thermal energy means that the molecules are moving faster, meaning higher temperature, faster molecules. So that's a concept that I always stress in this class. Higher temperature, faster molecules, and more degrees of freedom of the molecules. And thermal energy is a type of kinetic energy because it is the energy of forcing motion dependent on temperature. Then you have potential energy. So potential energy is stored, and there's different types of potential energy. There's the easy one, which we can understand, is gravitational potential. So if you hold an apple or hold a ball, and then you drop it, depending on its position, on how high you hold it, it has a different amount of potential energy. That equation is mgh from physics. What that means is it depends on the height. M meaning the mass of it, g meaning gravity, h meaning height. So basically, it is a measure of how much energy is going to be converted to kinetic energy after the ball is released, or after the force keeping it from moving is released. So if you hold it higher, it's going to create more kinetic energy as it gets dropped. Therefore, it has more potential energy. So it's the energy that is stored, the energy that is going to be kinetic energy. And also in potential energy, you have chemical energy. So chemical energy is the energy that's stored in bonds. And a best example of this is food. Think food. Because if you eat food, that's giving you energy somehow, right? The way it is it's being broken down, it's being metabolized into proteins, into amino acids, into carbohydrates, into sugars and stuff like that, into fats. And those molecules, those macromolecules, are being stored in your body. And then upon you needing to use them in the form of muscular movement or some kind of internal metabolism, what happens is the bonds break down and then they reform other things. And then those molecules are used for the metabolic process. So in that breaking down of the bonds, energy is being released from those molecules, and that energy is helping you to move. So that potential is turning into kinetic, but it's a chemical energy, not really nothing to do with gravity. So here's a breakdown of energy. So you have kinetic and potential. And then for kinetic energy, the one we learned about is thermal energy. These are not the only types, but you have thermal energy associated with faster temperature, faster molecules. Then chemical energy, which they say associated with positions of electrons and nuclei, whatever. That just means there's energy associated with bonds, bond energy, and the bond energy is released eventually, and then that energy is used to do our metabolic processes. So here's an example of some other forms of energy, of electrical energy, which is the flow of electrons, electrical gradient, stuff like that. That's how current works. That's why we get electricity. Then your heat, thermal energy we talked about, light or radiant energy. So you can excite atoms with light. So you can excite we'll talk about this more when we talk about electron. There's a whole chapter on electron. I think chapter 8 and 9 is a really electron heavy. So we talk about that. We talk about the spectra and everything like that. Then you have nuclear energy, which is potential energy in the nucleus, meaning the nucleus is going to burst, but then eventually it gets too much energy and it bursts, and it turns into kinetic energy since it makes the atoms move and break apart. Then you have chemical energy, which we talked about, which is a potential energy. Okay, so another important concept before we get really into the math is defining the system and the surroundings. So we're going to be using these words a lot. We're going to be using endothermic, exothermic. We're going to be using released and gained. We're going to be using the system and the surroundings. These are a lot of different terms. But basically, let's say we have a water, a glass of water with ice. Now, a glass of water with ice is the system. The system is contained by the glass of water. Let's say it has a lid on it too, so nothing can escape or enter. That's the system. The surroundings is everything around it. So if we say heat is gained by the surroundings, that means heat is released by the system. You see how they're opposites? So I'm going to write that down. And here's the hand warmer example. The hand warmer example, the chemical reaction is the system and our hands are the surroundings. So you can define the system and the surroundings as anything you want. So for ice water, let's just say ice plus cup of water equals system, environment equals surroundings. So that's a possibility, but you can define the system and the surroundings as anything you want. But in the question, it usually defines it for you. So you'll see what we mean by this. You have to really, the reason why we need to know this is because, one, to just understand it better, and two, to denote, is it a positive sign? Is it a negative sign when it comes to energy? If something is released by the system, that means it's a negative sign. If something is gained by the surroundings, that means it's also a negative sign because it is still exothermic because the system is releasing, gained by surroundings. If the surroundings releases something into the system, that means it's positive because the system will be gaining energy. So is there any questions on that? That's an important concept. No? Okay. All right. So now we will talk about the units of energy. So here's 1/2 mv squared. We're not going to cover it, whatever, but we know that kinetic energy depends on mass and velocity. So the main unit of energy that we're going to talk about, there's two of them. I'll just go to here, is the joule and the calorie. So joule, we've seen before. We've seen it in the ideal gas constant, the one that is 8.314. That's the joule. And that's in joules. But basically what a joule is the amount of energy required to move 1 kilogram a distance of 1 meter. So 1 meter is about 3 feet. Moving a kilogram is about like a couple pounds, right? It takes a decent amount of force. You gotta move it, right? Yeah. Then you have a calorie. So calorie, which we know is based on food and stuff like that, is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So if you think about those, I'm going to give you an idea of how, we'll learn about specific heat, but I'll give you an idea of how stubborn water is, or how much energy is required to change temperatures of water. A joule, think about this. A joule is 1 kilogram mass moving at a distance of a meter. You'd be like, all right, that's like one amount, whatever. But if you had to compare the two, think about what requires more energy. 1 kilogram moving at a meter, or increasing just a gram of water, 1 milliliter of water by 1 degree Celsius. Which one you think would require more energy? And I mean, the answer's up here if you know the numbers, but I guess I'll just answer it for you. Me personally, I would think that, all right, a joule is probably more. Moving a kilogram mass a meter, like I have to walk a meter, I have to like push it 3 feet, compared to just changing water, a milliliter of water by 1 degree. That should definitely be the joule is more. But actually, it's the other way around. So a calorie is actually 4 times a joule. So that's where you get this conversion of 1 calorie equals 4.184 joules, meaning that moving a 1 kilogram mass 4.184 meters is equivalent to the energy required to change the temperature of 1 milliliter of water by 1 degree Celsius. That's only a milliliter of water. So imagine a cup of water, or imagine a pot of water where you need to boil it. Think about how much energy is required for that. You need to change hundreds of milliliters by 100 degrees or even more. So that's crazy. That's or only 100 degrees, or maybe 75 degrees if you're going from 25 to 100 to boil it. But still, that requires a lot of energy. So water is what we call, it's very stubborn, but the really scientific definition is that it is a high specific heat constant. And what that means is it requires a lot of heat to change it at all. And we'll talk about that later on. But the most important thing is we're using these units, the joule and the calorie. Now, the last thing about joule and calorie is that a food calorie, I'm sure you saw this, a food calorie is different than the SI unit for the, well, calorie is an SI unit, but it's different than the calorie. It's different. So food calorie represents 1,000 of these calories. Because either way you want to look at it, a joule and a calorie, they're still very small units. They're not you can have hundreds of calories, thousands of joules, thousands of calories. And you see most of our measurements are going to be in kilojoules. And we'll have 10 to the 5th, 10 to the 6th calories, or even kilocalories. And the reason why is because they're just generally small units. Now, the kilocalorie for food is capital C. And that means 1,000 calories. So if you say you have a juice or whatever, or a snack, that is a 100-calorie snack.
I can hear him now.
Can you hear me now?
Yes.
Okay, great. Okay, so the food calorie has a capital C, and this means kilocalories, same exact thing. If you say your drink or your snack is 100 calories, that means it's actually 100,000 of these lowercase calories. So that's weird. That's like not sure why they do that, but I can guess it's because they don't want you to look at your nutrition label and be like, holy crap, I'm taking in 100,000 calories right now. They're just smaller numbers to work with if you use kilocalories. But why can't they just write kcal on it? Instead of confusing us with using the exact same word, the only difference is the capital C. That's weird to me, but I don't know why they do that. So here's an example of a nutrition label, and you can check any nutrition label you can find in your house that the C in calories is always capitalized. And for this example, it's 240. That means it's 240,000 calories. So yeah. Any questions on that?
Can you go back a slide for 1 sec?
Yes. Yeah, so food calorie, kilocal. And the main two units we're going to use are calorie and joule.
Okay, got it.
Okay, cool. All right, so energy exchange, we talked about this already. We have heat and work. So heat, we use the variable Q for heat. And in work, we use a lowercase w. Sometimes capital W, but lowercase w here. And it can be exchanged from the system and the surroundings. They both can. So the next thing we're going to learn about is a state function versus a not state function. Now, these are just definitions, but it's important to know which one's which. Now, a state function means that that it doesn't matter the path of the energy transfer. The only thing matters is the difference between the final value and the initial value. So what that means is, we use this example. Energy is a state function. So the path doesn't matter. It just matters where you end up. Now, in terms of energy, what would take more energy? Or his example, or if you go up this hill this way, when the zigzag path A takes 12 miles, if you go up path B, it's 5 miles. But the amount of energy required to reach the top is the same. You might be stupid and use more energy depending on whatever, but like the amount of energy required by you, by whoever's moving up is the same. And the reason why is because they balance out. The heat and the work balance out. So the equation, where's my pen? Let me get my pen. So the equation is, which we'll see in a second, is, hold on, this is slanted, which is E equals Q plus W. So the heat and the work balance out. If you go up this way, path A, the work is going to be a lot because you're going to be doing a force over a large distance. But the heat is going to be a little bit. Your body's not going to get too hot. Your muscles aren't going to move too much. Aren't going to be moving as hard as they are in path B, which is a lot steeper, but the work will be less. So there's that balance. And also there's a lot more that goes into it, meaning like your metabolism, the rocks, stuff like that. But the ground, the friction. But generally, heat and work, they balance out, and that's how they add up to energy. And energy itself is a state function, meaning it doesn't matter how you get there. If you take a helicopter straight up, you yourself aren't going to be using much energy, but the helicopter rotors, the helicopter gasoline is going to be using the same amount of energy to get to the top than if you took either one of these steps, even though it would be faster. So energy is a state function, meaning it doesn't matter the path taken. So there you go.
Heat.
Yeah. Question?
Is Q heat?
Yeah, Q is heat. Sorry. Yes, Q is heat. And you see right there, heat, Q. I'll write that down. Okay. So then you have internal energy. Same thing as energy is the state function. Just matters the final and the initial. So you want to figure out the change in energy. Change in anything is really the final value minus the initial value. We haven't really been talking about changes. That's what this delta means. So delta means change, final minus initial. We're going to be talking about that for energy, for temperature, maybe for work, but there's a lot of things you can use a delta for. Okay, so a lot of time, well, all the time in these examples that we do, we're going to be assuming conservation of energy, meaning the energy that is released by your system is the same amount of energy gained by the surroundings, or vice versa, meaning no energy is going to be randomly lost to the universe from our question in our problems. And we would, I mean, in reality, it is. It always is. There's no perfect conservation of energy. There is. All energy is conserved. But if we're doing a reaction in real time in the real world, we're not going to gain 100% of our energy that is lost from our surroundings to our system. Some of it will always dissipate into the environment. That's a given. Just like our percent yield is never 100. We'll always lose something. But what we can say is that in the problems we do, we assume that energy is conserved. So it's 100% of energy being moved from either one way or the other, and we're not losing any to the environment randomly. Hold on. Oh, that's just my cat. I heard a loud noise. I'm like, it's happening. Someone's trying to break in, but it's just my cat. I think she fell or something. Whatever. She's fine. Okay. So here is our here's our variables that we're going to use. We can use Q as heat, which is a thermal energy, work, W, and also keep in mind that Q and W are not state functions, meaning their value depends on the process. So delta energy it depends if you go high or low, or if you the final and initial. But if we look at this path again, the work required on path B, force over a distance, it's going to be a shorter distance. The force, you're still walking. It may be about, this is not the best example, but the work in B is probably going to be a little bit less than the work in A, but the heat will be more because you'll be generating a lot more heat to use your muscles to move up that. You'll be sweating a lot more doing B than you will on A. Even A will probably take longer, but you'll probably be using a lot more heat on B. So Q and W do depend on the path taken, but together, when they make energy, they don't. So these are important definitions in this table right here, just to understand positives and negatives, because we're going to be decoding these problems by saying there's positive. If it's positive, that means something the system gained. Negative, the system released. So just the terminology is that when we're dealing with heat, system gains heat energy. That's a plus. System releases heat, minus. For work, system gains work, plus system releases work, or doesn't have to say releases. the system could do work to the surroundings. That's also negative. That's a weird little thing. Sometimes if you say something does work on something else, that means the sign is kind of saying it releases work into that thing. So I hope that makes sense. And then you have delta energy, which is the system gains energy, system releases energy, plus and minus. So we'll be doing these examples, and you'll see what I mean. So first law of thermodynamics is that the amount of energy in the universe is a constant. So it cannot be violated. There's always a constant amount of energy. No energy is being just magically put into the universe. It's always being transferred. It's always being manipulated. The enthalpy, or sorry, the entropy is always increasing. That's just the disorder of the energy. But the enthalpy and the energy is always the same in the universe. And we'll learn about enthalpy also today. Okay, so let's do example.
Can you go back for a second?
Yes, I can. This one?
Yeah.
Okay.
Wait. No. I had right before where we were, yeah.
This one?
No, the one, like, yeah, that one with the
This one?
definite. Yeah.
Okay. I guess either way you're going to see the answer, but we can do it together for the example. All right, are you good?
Yeah.
Okay, cool. And also you can the previous slides you can see on the side. So if you missed something, if you look closely, you could probably read that. But anyway, so yeah, always stop me if you have questions. That's good. Okay, so for this example, let's read the question carefully. Calculate the delta E. All right, so we're probably going to use delta E equals Q plus W. For the surroundings, if an exothermic reaction releases 15.6 kilojoules of energy of heat into the surroundings, and where 142 joules of work is done on the system. Okay. A lot of stuff going on. So
I think it should say 142 kilojoules now.
yes, there's a typo. No, there is no typo. Yes, here it says point.
Okay, we need to
0.142
convert.
kilojoules.
Okay, yeah.
Okay, yeah. So we know that we could do it either way. We could just cut right to the chase, or we can do the energy of the system gained by the system equals the negative energy of the surroundings. But let's talk about the surroundings. The delta E surroundings. Put Sir. This is going to equal Q on the surroundings. So I'll put Q Sir plus W Sir. So what we have is exothermic releases this much heat into the surroundings. That means if I am the surroundings, I am gaining that much. So I'm going to put positive 15.6 kilojoules. In the perspective of the surroundings, again, 142 joules of work is done on the system. So if it's done on the system, that means it's being taken away from the surroundings. So it will be minus 0.142 kilojoules because we need to convert all to the same unit. And then this answer will be positive 15.5 kilojoules. And this is the change in energy of the surroundings. So I did that directly. Now, they did it a little bit different. I'll explain that in a second. But does everybody understand what I just did and how I explained it?
Mm-hmm.
Okay. Anybody else have any questions? Because that's important to understand the perspective of the surroundings, you being the surroundings versus you taking the perspective of the system and writing the equation. So you get the same answer every time. So here's what they did. They said, all right, I know that based on the first law, the energy of the system is the negative energy of the surroundings. It's asking for the energy of the surroundings. But if I find the system first, I can just negative it. Me personally, I wouldn't do that. I would do what I did. But either way, it works. change in energy of the system. Q system. If you look at the example, it's exothermic, releases into the surroundings, meaning Q system is going to be negative. And then where you have 142 joules of work is done to the system, that is going to be positive because it's being done to the system, and we're taking the perspective of the system. So then your answer will be negative 15.5 kilojoules done to the system. If you negative that, you get positive that's done to the surroundings, and you get the same answer. So yeah, any questions on that before I continue? Yeah.
I'm just a little confused as to why two separate, I guess, two separate things, heat and work, are measured in the same unit.
So heat is a type of energy, work is a type of energy. So they're both, that's a good question. They're both types of energy. So heat is thermal energy, which is a type of kinetic energy. Work is also a type of energy, by definition, the force over a distance. Now, in an equation, in a chemical reaction, there's going to be heat involved, and then there's going to be movement of molecules involved. There's going to be two sources of energy in a chemical reaction. Or really, in anything, there's two sources of energy. If you think about it, if you work out, if you lift a weight, your muscles are generating heat and releasing that heat into the environment. And the second source of energy is the work being done by your muscles to use a force and move a weight over a distance. So if you add both those sources of energy up, you get the total change in energy. So they're both types of work. So that's a good question. Cool. All right, anything else? Ask, can you mute your microphones if you are not talking?
Professor?
Yes.
So in this problem, because you're looking for the change in energy for the surroundings, you a way you can look at this problem is by acting like you're the surroundings, and then.
Yes, that's exactly right. That's exactly right. You can pretend if you want to be in the perspective of the surroundings. If you're being asked for the surroundings, a lot of times, most questions you're going to be asked for calculate the change in energy of the system, but this was just to get your mind in the right direction. But either way, you need to be conscious of your perspectives and the way the question is worded. Okay, so all good questions. Moving on. So we have heat exchange, whatever. We know this already. It's just redundant. Okay, so heat can be exchanged. We know that. Now, there is a specific level or specific exchange rate that heat is exchanged with comparison to energy. So that was a bad way of saying it, but there's this thing called the heat capacity. The heat capacity is measured in joules per Celsius or joules per Kelvin. It is the capacity of heat that something has. Wow, no, really, it is. But what that means is it's a measure of the resistance that a substance has to the change in temperature. So, in other words, how many joules does it take for that substance to change by 1 degree Celsius? That is the specific, or they call it specific heat capacity, or just the heat capacity of an object. And it varies, whatever substance you're talking about. Every compound has a different specific heat capacity, or even every substance, different metal alloys have different heat capacities. It varies per substance. And you can measure the heat generated by a system or by a substance based on its heat capacity. Constant. It's a constant. Sometimes you can find it, but the constant varies for each individual type of substance. And the equation is QCat, even though there's no A. The delta looks like an A a little bit. So it'd be Q equals C, which is our specific heat capacity, times our delta T, which is the change in temperature. So, for example, if and Q could be the same for two different. The amount of energy and heat, the amount of energy, the heat energy could be the same, even though the temperature doesn't increase as much. So if that doesn't make sense, I'll use this example. So I said before, water has a high heat capacity. So meaning, if you charge water, put a lot of heat into water, such as the sun, into an ocean, you put a lot of heat into water, the specific heat capacity of water is high, the temperature change would be low, and you put in a certain amount of heat. If you put that same amount of heat to sand, and I'll explain, use the beach example. So if you put a lot of heat into sand, the specific heat for sand is low, but the temperature increase will be a lot. So if you look at water, if you go to the beach even now, June, it's really hot. And if you go to the beach now, who went to the beach so far already? Well, I'm not going to, well, some of you.
I heard it was cold.
Yeah, exactly. It's freezing. The water in June, even though it is the hottest, June and July is like the hottest of the summer. You get 100 degrees sometimes, and the water is still freezing. So for someone who grew up on the shore, the best time to go to the beach is late August, even early September, where it's still like 80 degrees outside, because then you're going to have the warmest water. Because the water is so stubborn, has such a high heat capacity, it takes months of direct hot sunlight to change the temperature of the water. I know it's a lot of water, it's a big ocean, but to change the temperature of the water by a couple of degrees, by maybe 10 degrees, takes months of direct sunlight. That means it's a very high specific heat. It can take a lot of energy and not change temperature. It is a really good resistance to temperature change. Now you look at, question?
Does it take longer because it's salt water versus fresh water?
Yes, that is true also. Yeah, because there's more intermolecular forces. And the reason why is because of intermolecular forces. Hydrogen bonds, and there's different ions in there, so that's why. But either way, even if it was fresh water, it still takes a long time. You take a big lake, the same thing will happen. It'll take months for it to warm up. That's a good point. So now let's look at sand. Sand is just rock. And sand and rocks have a very low specific heat. If you go on a 100-degree day in June is a terrible time, or even really hot, 80 to 90 degrees, terrible time to go to the beach, because the water is going to be freezing cold. The sand is going to be burning hot because it has a low specific heat. That means you put energy onto it, it will directly be that temperature almost immediately. Maybe take 10 minutes to heat up, and your feet will burn. And then you go into the water and your feet will be freezing, and there's no medium. So the best time, early September or late August, when it's like nice humid 80s. So and we're not crazy amount of sunlight. So it's a good medium between the both. So yeah, you could use the same equation for both. You could put the same amount of heat from the sun onto sand and the ocean water, and you can still get the same Q value, but with different specific heat and a different change in temperature, and they balance out. They're inversely proportional, if you will, because if this one's higher, if C is higher, delta T is going to be lower. So, okay, we talked about this already. Factors affecting heat capacity. It depends on the amount, obviously. Usually we talk about per gram or per 100 grams, but if you have a large ocean of water, it's going to take more energy for it to change. But more importantly, the constant the constant doesn't depend on the amount of matter, but the heat capacity of an object in general does. But of a substance, the constant depends on literally what the object is, the type of material. Whereas if it's water, is it sand, is it rocks, is it aluminum, it's all different. And there's a table right here of the specific heat capacity for different elements and compounds. So water you see is the highest, 4.18. And there is things higher than water, but water is generally very high in comparison to different metals and other things in the periodic table. My cat's going crazy again. Hold on. She jumped on the computer. Okay, so then you have that constant. Then you have the molar heat capacity, which in chemistry, they just like to use molar to make everything in a mole, right? It's the same thing as heat capacity, but it's the amount of energy, the amount of Q, heat energy, required to change the temperature of 1 mole by 1 degree Celsius. Whereas the joule is the amount of energy required to change 1 milliliter of water by 1 degree. So this is, let's just make it a mole. So you can see how you can figure that out. If you were given a specific heat by gram, how much is the molar heat capacity? Just multiply it by, or find out how many moles is 1 gram, and then multiply that to figure out how many is a mole. So you can figure that out. And you'll see there might be questions on the homework like that. But anyway, so here is the total equation for using specific heat capacity. Here's the main one you're going to use. And this is dependent on the mass. So the one we looked at before, Q equals C times delta T, that is just dependent on 1 gram. So it's just saying that there's 1 gram of substance, changes the temperature with a specific heat capacity. What's the heat that was required to make it that temperature? But the total equation, not depending on mass, or depending on mass, but the mass varies, not just 1 gram, is Q equals MCAT, which is the equation. So Q equals the mass times the specific heat capacity, which in this constant is a little bit different than heat capacity. And that is required, that's per gram. And then you have the temperature change, which is in Celsius change, depth temperature change. Now, one of you could be like, oh, what about Kelvin? Are you always using Kelvin? That's confusing. But this is temperature change. So if you remember that the difference between Kelvin and Celsius is only an additive factor of 273, the temperature change for Celsius and Kelvin is the same thing. Whereas like, so like 1 Celsius versus 2 Celsius, the difference is delta T equals 1, 274 Kelvin versus 275 Kelvin, the delta T is still 1. So either one is okay for change, but not Fahrenheit. Fahrenheit is different. Okay, let's do this example. So how much heat is absorbed by a copper penny with a mass of 3.1 grams, whose temperature rises from -8 to 37 when C for copper is 0.3885 joules per gram. Okay, so Q equals MC delta T, and let's just solve. So Q equals the mass, which is 3.10 grams. C is 0.385. And we'll look at units, joules per gram. And then actually this should be joules per gram Kelvin. Or actually, no, it doesn't matter. Or joules per gram Celsius. Whatever, doesn't matter. It's not written there, but whatever, we can figure it out. So delta T is 37 minus -8. So 37 minus -8 is, that's going to be 45. So it would be 3.1 grams times 0.385 joules per gram times 45. And our answer is going to be, yeah, they messed up. There's supposed to be Celsius there. I knew it. All right, so then your answer is going to be 53.7. Move my camera out of the way. Oh, no. 53.7. But yeah, you can see 53.7 right there. Cool. Okay, any questions on that one? So this is like a plug and chug. You plug in your values and then solve. Some questions you might get Q, and you might be being asked for M or C or delta T. You might have the final temperature, but you might need to find the initial temperature, things like that. sometimes there might be questions where it says identify the substance. So for that, you calculate C, and then you refer to a table, and a table will be given, and then you refer to it and then see, oh, it's aluminum, and then you can figure that out. Okay, so now we're going to talk about more things about work. We know about heat gained by the system is heat, whatever. So, the transfer.
Professor,
Yes.
I'm not sure if I just wrote this down wrong in my notes here, but I wrote that heat capacity, right? Q
Yeah.
is equal to C times delta T.
Yes, that is a thing. So that is a
Okay.
general equation. That's this one.
Yeah.
Right?
So then if you take that and you plug that into the heat energy, the Q equals MCAT, the delta T just cancels with the Q. I mean, with the other delta T, and the Q cancels with the other Q, and you just have M. I don't get that. Like, is
So-
that the same C? Is
They're the
C
same
and C sub S the same thing?
No, so C and C sub S are a little bit different.
Okay.
Right. So they're the same equation. This is just a general equation. And then to make it more specific, you make this C into a constant per gram, which, yeah, you make it per gram, and then you add mass and multiply by mass, you get a modified version of it. So we're going to use this one. They're the same. They're the same thing, but we're going to use this one because we're going to have an object of a mass. And the other one, we were assuming it's 1 gram. 1 gram of substance. So this is the complete equation. So just use this one.
All right.
Okay, cool. All right. So thermal energy transfer. So ice, or this is metal in this case. But let's just talk about examples. Now, you have a block of metal that's heated, 55 degrees Celsius, submerged in water, initially initially at 25 Celsius. The temperature change, there's going to be 2 things happening at this point. So you put the metal into the water. Please mute your microphone. All right, I did it. Oh no, my cat's home. She sees reflections on the wall, and then she goes nuts. She like jumps on the wall. But so we're gonna have a lot happening when you put a hot metal into a cold water. The metal temperature will go down, and it'll go down depending on the specific heat of the metal, how much metal there is, and the temperature of the water. That'll determine how much it goes down. The water will go up because you're putting a hot substance into cold water. The water will go up, and eventually an equilibrium will be reached, a temperature by both of them. Let's say it's 30, 32, 31. It'll probably be around closer to 25 than it is to 55 because water, high heat capacity, makes it stubborn. It's not going to want to change temperature as readily as the metal is. The metal will change temperature very quickly. So it'll probably be 30, 31. And there's a lot happening here. You can figure out that equilibrium temperature using the Q equals MCAT equation. You can make 2 Q equals MCATs, one for metal and then one for water. And you can equate them because you know that the energy released by the metal is the energy gained by the water, or vice versa. So positive one equals negative the other. And it doesn't matter which one has the negative sign. So what you can do is you can do that, and you can move my camera out of the way. Screw the camera, whatever. It's done. All right, so what you can do is the metal has its own equation. So it depends on the mass of the metal, the specific heat of the metal. Delta T would be would be T final minus 55. The mass of the water has a mass, the water has specific heat, 4.184, and then the temperature of the water would be final minus 25. So Yeah. So you can use that to solve your final temperature. Basically just equating 2 equals MCATs in an energy transfer. So that's the thing. Any questions on that? Is just using the same equation and making them equal. No? Okay. All right. So then we have work can be involved with this kind of different thing now. But now we can equate work with gases. So we're combining chapter 6 and 7 right now. So there's an equation that the work is equal to the external pressure, that's why it's negative, external pressure of the gas times the change in volume of gas over a change. So let's say something's being expanded, right? Let's say that there's a lot of pressure this gas is doing on the piston, and the gas pushes on the piston and does work to the piston by increasing the volume of the gas and moving the piston along a distance. That is doing work. We can calculate that work by force times distance, or we can calculate it specifically with gases by the pressure, because the pressure is the same thing as the force, times the change in volume. Well, the pressure is proportional to force, and for volume, it's proportional to the distance when we're talking about gas expansion, kind of like the distance it expanded. So you can kind of think about this as a work of the gas is like a modified force times distance equation, but it's pressure and volume. So keep in mind, another thing is with this equation, we're going to do an example with this one, but keep in mind that work is usually measured in joules, right? Now, this equation, work equals negative P delta V, will give you an answer in ATM, if we're using ATM for pressure, times liters. They give you an ATM per liter. That's not a joule, right? So we need to convert these to joules at the end, because sometimes this will only be one step of the equation. So let's say you have calculate the internal energy change when you have a certain amount of heat, and then you have a gas, that gas is a certain amount of heat, doing some pressure, changing by volume, or expanding the volume. You're going to have to find work using this equation, add that work to the heat and in the same unit, and then that will equal the internal energy, E, right? With E equals Q plus W. But the W will actually be expressed as this. So that's a possibility also. For that possibility, then the conversions will be given on the exam, but this is the conversion. 101.3 joules equals 1 ATM liter. So really, you multiply your number, whatever your ATM liter is, by 101.3, and you get the joules. So let's do an example. We'll cut this out of the way. Okay, so I think this is a simpler example, but let's do it. So calculate the work done when a gas expands from 46 to 64. So delta V is going to be 64 minus 46. And that's going to equal what? 18 liters at a constant external pressure of 15 ATM. So P equals 15 ATM. So W equals negative 15 times 18, and that equals a number. And that number is 270. So negative 270 liter ATM. Then we take negative 270 liter ATM, multiply it by 101.3 joule per liter ATM. You see how liter and ATM would cancel out, and joule would be your final value, and you would get 27351 joules, or by sig figs, which nobody cares about anymore, it would be negative 27 kilojoules. Cool. All right. So does that make sense? That this work equation with the negative P delta V will give you a liter ATM value, and you convert that to joules. But this may be one step in a longer problem, which we'll see maybe, which will be in the homework. Okay, any questions? Because we're gonna switch gears again to now we're gonna talk about chemical equations and how this relates to chemical equations. No? Okay. All right. So there's a new thing. It's called enthalpy. Enthalpy. So enthalpy is basically the energy and heat that is associated with a chemical reaction. So associated meaning could be released, it could be gained, but here is how it's denoted as delta H. Think about it as a heat of a chemical reaction. Delta H could be either positive or it could be negative. If it's positive, it's endothermic. If it's negative, it's exothermic. So I just gave you the answer for number one. Is it endothermic or exothermic? It's exothermic because the enthalpy is a negative sign. Okay, so now here's a question that this is saying, I'm going to give you this to do on your own for a minute or two, but this is saying that this combustion reaction of propane releases, because exothermic, releases 2044 kilojoules. How much energy is released when 50 grams of propane is combusted? This is saying that 1 mole of this reacts with 5 moles of this, 3 moles, and 4 moles to make this much energy. How much is 50 grams? How much energy is released when 50 grams is combusted? So right now it's 10:01. I'll give you till 10:05 to figure that out. And you could ask questions, of course, but yeah, try it. Give it a shot. I should do it too, so I know what the answer is.
So should the change in H not be that different?
It won't be tremendously different.
It would be.
It won't be tremendously
Oh, it
different.
won't be, because if you calculate the molar mass, then it's not that much different than.
Yeah,
the
that's
50
exactly how you
grams.
do it.
Okay.
Okay, so it's 10:05. Hopefully, most of you guys understand how you arrive at the answer. So what you would do is you'd see that, all right, 1 mole of propane releases this much energy. Find out how many moles is 50 grams. The molar mass of propane is 3 times 12, all approximations, of course, 3 times 12 plus 8 for the hydrogens, and you get 44 grams per mole. So 36 plus 8. Yep, I did my math right. So then 44 divided by, 50 divided by 44 is going to be 1 point something. I just did the math in the calculator and then just erased the history. So that's nice. So it would be 1.136 moles. And then you know that 1 mole makes this. So then 1.136 moles times negative 2044 times 2044, and that will be negative 2323 kilojoules. Or if you want to go by sig figs, technically you'd have to make in 1 sig fig, which is why sig figs is dumb. So it's going to be that. Okay. Any questions on that? Hopefully it wasn't too bad. Okay, so that's basically how you do enthalpy. And let's do a more difficult example. So there really isn't much more to it than that. It's like one more equation, and then we'll do some examples, and then we'll learn Hess's law, and then a couple other things, and that's it. So rocket propulsion. All right, so here's an equation for rocket propulsion. When the reaction consumes 10 grams of liquid N2O4, it releases that many kilojoules of heat. What is the value of delta H per mole? That's the thing, per mole of N2O4. That's what it's asking for this reaction as written. So again, I will give you 5 minutes until 10:12 to complete this one, and then we will come back and go over it.
Professor?
Yep.
All of today's material is going to be on quiz next class too. I mean, test next class too.
Yes, except for Hess's law. Where is Hess's law? There it is. So after 42. Yeah, after 42, it won't be.
Okay.
So everything up to 42. Slide 42.
Okay, great. Thank you.
And another thing I'm going to do is just like I did for the first exam, I'll post a little like review video just to like go over the concepts. I'm not sure how much of a help that was, but I don't know. 10 minutes just to summarize everything, what you need to know. All right, let's do this example now. So, all right, so we know that 10 grams releases that much. So let's find out how many moles are in 10 grams. So 10 grams divided by the molar mass of N2O4. So N2O4 is N2 is 28 plus O4 is 92. So it's going to be 92 is the molar mass. Let me double check that. Yeah, 92. Okay. So then we have 10 divided by 92. That's going to be 0.109. If you want to round. That's going to be how many moles reacts and releases 120, whatever, make this negative 124 kilojoules. So we know it's negative because releases, that's a key word. So what is delta H per mole? So if we know that 0.109 moles makes 124, releases 124 kilojoules, then 1 mole releases X kilojoules. So you can cross multiply and solve this. The way I think of it is proportions. So you can cross multiply and think however you want, and you would get 124 divided by 0.109, and you would get negative 1,138 kilojoules. Did everybody get that? Hopefully so.
No, I divided it the other way.
Did I mess up? Let's see. Yeah, it would be that because let's say you do this, you move X over here, multiply by negative 124, divide by 0.109. So then you would get 124 divided by 0.109 to get to X. Does that make sense if you cross multiply? So it'd be X times 0.109 equals negative 124, and then divide by 0.109. Then you'd get that. Okay. Anybody else have any objections, or does that make sense? Or questions?
Just leave it up for a sec so I can copy it down.
Oh, what was that? I couldn't hear that.
Can you just leave it up for a sec so I can
Oh,
copy
okay. Yeah, sure. No, just kidding. No, I'm kidding. Here you go.
it? Okay.
Okay, cool. All right. So enthalpy, and here's the definition of enthalpy: the sum of the internal energy of the system and the product of pressure and volume. So basically, it's the reaction, it's the energy associated with the reaction. Because in a reaction, you're going to have internal energy and you're going to have pressure and volume energy that's involved with that. So it's a sum of those. Basically the work. So where have you seen PV before? That's when you've seen work. That's when you've seen W equals negative P delta V. This is a form of that where you can kind of say, all right, the energy associated with a reaction is the energy of the reaction plus the work done by the reaction. And that's true as well. And enthalpy is a state function. So it doesn't matter how you get there. It just matters the final state and the initial state. So enthalpy and energy are both state functions. So something that's important is the enthalpy. Oh yeah, I don't know if we're going with that, but basically the enthalpy of the reaction at a constant pressure is the same as the heat of the reaction. Because think about it, if you have enthalpy is dependent on the heat and the change in pressure and like the pressure value. If you have a constant pressure, basically it's not changing. The volume's not going to change. So then you have the heat of the reaction is only dependent on the heat of the reaction and not the work. So you have delta H equals Q at a constant pressure. So that's one thing that's important, and we're going to use that definition to solve several problems. So yeah, we know endothermic, exothermic. We covered that already. So enthalpy of combustion. So let's do this one. This is important. So we've seen this combustion before of propane. So consider the combustion of propane. Also, we already used this information here, that enthalpy can be used as a conversion factor. We already did. In the previous examples we did, where we had the amount of enthalpy per mole of propane or the amount of enthalpy per 10 grams, whatever, we already kind of used it in an equation like we would a conversion factor. So here you have the combustion of propane again, the same equation. We know that 1 mole of propane releases negative 2,044 kilojoules. Now, if we were looking for how much heat is evolved in the, but I guess evolved is a good word too. How much heat is released in the combustion of 13.2 kilograms of propane. So we know that 1 mole releases 2,000. So 13 we'll just do the math over here. 13.2 kilograms. So that's 13.2 times 10 to the third grams. How much energy does that release? So we can figure out the molar mass of propane, which, if you recall from the last question, it was 44. So we have 13.2 times 10 to the third grams divided by 44 grams per mole. And that's going to be a lot of moles. We'll figure out how many in a second. 13.2 times 10 to the third, or times 1,000, divided by 44. And that is exactly 300 moles. 300 moles of C3H8. So if that's the case, then the amount of energy released by combusting 300 moles would be 300 times negative 2044 times 2044, and you get big number. You get 6.132 times 10 to the 5th kilojoules. And that's what you get. So let's see what they got. Yeah, well, negative. Whoopsie. Negative. So that's going to be, they got negative 6.12, whatever, they rounded. They sig fig rounding, whatever. You get the same thing. Oh, that's because they had 44.09. That's why. Okay, so is there any questions on that? So basically, you're using this enthalpy in the equation as a conversion factor. Sometimes the equation might not be as simple as per 1 mole of methane, of propane. Sometimes you may have 2 as a coefficient here. And you notice all the equations are balanced. So balancing is still going to be a thing on this test. And I might give you a combustion that isn't balanced. And you have to balance it first, find the enthalpy per mole, find the enthalpy per 500 grams or whatever, and then maybe do some other stoichiometric things with the equation. Or maybe I give you a pressure and a volume, and you have to find the work in the reaction. Or there's a lot of different things you can do with these type of questions.
Professor?
Yeah.
I forget, last exam, do we get a formula sheet?
Yes. Yeah,
Okay.
It'll be on the back. You didn't have to use it last time because there wasn't that many formulas. But this time, there is all those laws. This chapter has a lot of formulas, so you'll be getting a formula sheet.
Is it up anywhere right now for us to?
Did I post the exam 1 answers yet? Did I not? I don't know if I did. If I didn't, then I'll post that, and it's the same formula sheet.
Okay.
Okay. Also, wait, never mind. The practice exams. It's on those.
Okay.
So yeah. Oh yeah, and definitely there's 2 practice exams that are on Moodle. I'll show you them afterwards. I'm going to pull them up on my screen now, and I'll show you them later.
Exam 2, 20.
Yeah, exam 2, fall 2017 and 2018.
Yeah.
Yeah.
Okay.
So there, and with the answers, so you can take a look at that. Okay. So I think those exams, one of them might have Hess's law on there, but it's not going to be on our exam.
Yeah.
Okay, practice this. When 1 mole of methane is burned at a constant pressure, that many kilojoules of energy is released as heat. Calculate delta H for a process in which 5.8 grams of methane is burned at a constant pressure. Okay. So a very similar problem. We can do this together. So if we have 1 mole makes negative 890, meaning it's released, because it says released, then 5.8 grams, figure out how many moles of methane, CH4, that is. So methane has a molar mass of 16, 12 plus 4. So 5.8 divided by 16 is 0.363. That's going to be moles. So then we know that. Then we know that negative 890 kilojoules is 1 mole. Moles will cancel, and we get negative 323 kilojoules. Boom. So yeah, not so bad. There we go. Good. That's the answer. There's no answer here. Oh. Okay. Well, that's the answer. All right. So moving forward, there's this thing called calorimetry. So we already understand the equation. So calorimetry is basically is one example of it. There's 2 types. There's a coffee cup calorimeter and a bomb calorimeter. They both do the same thing. They use a thermometer, and they react. They either place a hot substance into water, or really change the pressure of something. And in order to determine how much heat and how much energy is associated with that thing. So calorimeter, think about it, a calorie meter. That's how they figure out how many calories are in our food. They break it down and see how much energy it takes and how much heat it takes for it to burn down, or for it to react, or to change temperature. So that's how they figure that out. And they use the Q equals MCAT equation. So you can change, determining based on the heat of the solution, the mass of the solution, the specific heat of the solution, and temperature. You can figure out the energy, and then that energy could be equated to delta H of the chemical reaction. And then from there, you can get a calorie count. You can just do a conversion, and you can get a calorie count for whatever you put inside the calorimeter. So that's just one device. It sucks, honestly. No one uses this anymore. Coffee cup. It looks stupid, right? That's not a real thing. In the lab, you do that in like Chem-1 lab, but there's like high pressure devices that could figure this out in like a second if you in like a real laboratory that determines food calories and stuff. So this is just like a thing you do in lab. This type of calorimeter was invented in like the 40s. So like it's very dumb, but the equation still works. So I don't even know why they use irrelevant examples anymore. I need to write my own textbook. I don't want to do that, but as long as I get paid for it, I'll do it. But whatever. So we could do this example. So what is delta H of the reaction per mole of magnesium for the following reaction? And this looks pretty sloppy, so I'll do this. So you have this reaction with magnesium reacting with hydrochloric acid to create magnesium chloride and H2. This is a single replacement reaction. If 0.158 grams of magnesium reacts in 100 milliliters of solution to change the temperature from 25 to 32, assume specific heat capacity of water is the 4.184 joules, and the density of water is 1 gram per milliliter. So yeah, this statement's true. So the question says that the reaction wait, does it even say that? How are you supposed to know that? So let's see. So if that reacts with that, the solution changes temperature. Okay, so the magnesium is releasing heat into the solution. So, and that's absorbed by the solution. So the magnesium releases the heat, and the solution absorbs the heat. Basically, like we were doing before, if you remember that example where you take the hot metal and put it in the water, what's the temperature change? That's what we're doing here. So this work is really sloppy, but basically, let's just do, yeah, let's just do this out normally. Yeah, okay. So what we're going to be doing, put this over here. This is a mess. So what we're going to be doing is we're going to be equating our heat of a reaction to our enthalpy of reaction by using our Q equals MCAT. So we can figure this out. All right, so we know that for our solution, Q solution equals the mass of our solution. Now our solution is 100 milliliters. Since it's water, it's 1 gram per milliliter, so that's 100 grams. 100 grams times the specific heat for water is 4.184 times the change in temperature, which is 32.8 minus 25.6. 32.8 minus 25.6. That's 7.2. 7.2. And you multiply those together, you get 100 times 4.184. You get 3,012 joules, or 3.012 kilojoules. And this is for, this means the reaction with 0.158 grams of magnesium. Now, for that much magnesium, you first need to figure out how much moles, because the question being asked is, what is the enthalpy per mole of magnesium, per mole? So 0.158 divided by the molar mass of magnesium, which is 24.3. You can look at the periodic table for that. That's just one of the ones I know. And you get a very small amount. You get 0.0065 moles. So if we have, let's do the work over here. We're moving over here now. So we have 0.0065 moles times, we know that, wait, we don't know that 1 mole. Hold on. We can do it a different way. So we know that there are different ways to do this. But let's just do the proportion. So we know that 0.0065 moles is responsible for 3.012 kilojoules. Then how many kilojoules is 1 mole responsible for? X kilojoules. Then you divide, you do 3.021 divided by 0.0065, and you get 463.4 kilojoules per mole. And this is true because also our equation has 1 in here. 1 mole in here. So is a good point. If this equation was, let's say, a 2 in front of magnesium, that means per mole of magnesium, it would have to be divided by 2. So that's a key thing. If you want to go, it would have to be, you doing from this equation would be, if they gave you, actually no, for in the equation, if they gave you delta H of the equation and you wanted to figure out the delta H per mole of magnesium, you need to divide that delta H by 2 if there was a 2 in front of the magnesium. So it all depends on the molar ratio. If they asked you about HCl and they gave you per mole, it's 3 kilojoules. That means in the equation, it's actually 6 kilojoules. So just keep in mind that the molar ratio also matters. So yeah, you get, also this is being released. So you get that. Yeah. So they got it in joules per mole. We just did it in kilojoules per mole. This would be negative. Let's make it right. Sorry, I'm like boring. I feel like I'm boring you. This example is just boring. But okay. Any questions? So you're using Q equals MCAT, and you just go through the math and you figure it out. And they did it in joules per mole. This is really sloppy. I'm sorry. I think the formatting messed up. Yeah. Okay. So question. Would you guys want to keep going and finish chapter 7? Because here's my thought process. The remaining part of chapter 7 is on the homework. I think we should go over it, but it's not going to be on the test. So I think we should go over it, at least go through most of it. We have a lot of time. Oh, it's only 10:33. Yeah, we're going to go over it. So sorry, I was about to ask you a question, but I just made an executive decision. But Hess's law is fun, and you'll see what I mean. So basically, in a lot of these reactions, there's intermediate reactions. If you want to get from, let's say, if H2, so let's say H3 is our reaction. So this is a bunch of energy, is a diagram, right? What this diagram is saying is that there's 3 reactions here. There's reaction 1, which is A plus 2B, and it gives you C. And that goes a positive enthalpy. That means it's an endothermic. Then there is equation 2, which gives you from C equals 2D, which means it's exothermic. The enthalpy goes down. What it's saying is the sum of both of those equations happening gives you a net change in enthalpy that is negative. So in other words, these 2 equations are intermediates of the final product. If you add the enthalpies of those intermediates together, you get the enthalpy of the product, of the final product, the final reaction. So it's the enthalpy 3 equals enthalpy 1 plus 2. Basically, many reactions can add up in certain ways to become one reaction. That's how a lot of these things work in organic chemistry, where you have multiple intermediates that are transforming to create a new product. And you could have 3 or even 4 equations. So there is a way to figure this out. You can figure out the final reaction and the final enthalpy of that reaction using a set of reactions. So you can read this on your own. We're just going to do an example. Actually, no, this is important. Sorry, this is important. So there's a bunch of different things. So standard state is when you have 1 atm and 25, kind of like STP, but STP is 0 Celsius. Or sorry, is 0 Celsius. But for standard state, for enthalpy, you have room temperature, which is 25 Celsius, 1 atm. And a substance with a concentration of 1 molar, but that doesn't really matter right now. Then you have these 2 types of constants that are specific for different types of substances. One of them is called the standard enthalpy change. So it's the enthalpy change of a reaction at a standard condition. And those are listed in tables. Then you have a standard enthalpy of formation, which is the enthalpy of formation of a specific reactant or product or something, some compound, at standard states. So and it makes sense that the enthalpy of formation of an element, such as O2, such as such as magnesium, whatever, is 0 because they're just there. It requires no energy to make them. They're just there. And there is here's a table with all of them. So you see like F2, O2, Na, they have 0 as our enthalpy of formation because there's no energy required to form them, no heat because they exist. But there is energies to form other compounds. Now, these can be used in several ways, and we'll talk about it now. So there's one way, if you know the enthalpy of formation of the products and the reactants, you can use this equation to find the standard enthalpy of the reaction. So here's the equation. The heat of the reaction, the standard enthalpy of the reaction, is the sum of the standard enthalpy of formation of the products minus the sum of the standard enthalpy of formation of the reactants. So products minus reactants gives you your standard enthalpy of the reaction. So it's the sum of products minus reactants. So yeah, so let's do an example. So let's say this reaction, right? CO is a product. So you find the standard enthalpy of formation of CO. If you go here, it's negative 110.5. Great. Negative 110.5. And then you would do minus graphite, because graphite is a product, is a reactant, sorry. Graphite is 0. Cool. So minus 0, minus 1/2, because the coefficient matters, minus 1/2 of oxygen. O2 is also 0. All right, so you get 0. So the answer is negative 110 because it's the products only. Everything else is 0. But sometimes they may not be 0. But that's just how you would do it. And don't worry, we'll cover this more after chapter. And you won't in the homework, it'll make sense. But I'll cover this more after the exam. I noticed there aren't many examples here. But that's the idea for Hess's law, is that you can do products minus reactants, but also you can do reactions added together and subtracted together to get to your enthalpy of a specific reaction. So here's what I mean by that. Oh, my button just fell out of my keyboard. All right. So I'm going to get rid of that. Okay, so we're going to do this one where this is a standard Hess's law problem. You are given these 3 equations in black. Nope. You are given these 3 reactions in, oh, damn it. Hold on. Okay, cool. You're given these 3 reactions. Your goal is to find the reaction in blue. Here's what we're going to do. The way you can do that, and each one has an enthalpy of formation. What you do is you are adding, subtracting, multiplying, whatever you want to do to get the coefficients of the 3 equations to line up with the reactants and products of the main equation, and then add them all up at the end. So you're modifying the equations for the products and reactants to line up in the same number, and the ones that are not there to cancel out. So if that doesn't make sense, we'll do this example and we'll show you how it's done. All right, so make sure it's balanced. Then go, just like we do for balancing equations, element by element or compound by compound. CH4 gas. Find that here. CH4 gas. Is it anywhere else? No. Is it where it needs to be? No. CH4 gas in our target, so this is our target, not target, is in our reactants. In the equation 1, well, the label is equation 1, 2, and 3, it's in the products. So what I need to do is flip it. So let's look at 1 prime. We flip it. CH4 gas yields CSGR, that means solid graphite, plus 2H2 gas. And then since we flip it, we're also flipping the sign of our HF. This means it's positive 74.6 kilojoules per mole. Does that make sense? Does that make sense why I did that? If not, please ask questions. That's the whole idea of what we're doing with Hess's law.
I understand what you did, but I don't understand how in the end it's gonna help us figure.
Okay. I guess we'll just see. We'll figure that out then. So you'll see how it works out. There'll be like oh, I get it moment. So
Okay.
All right. So just stay tuned. So now let's look at the next thing. So we got this CH4 is done. 2O2. All right. There's O2 here, and there's 1/2 O2 here. And that's kind of complicated. I don't know what to do. Maybe I might multiply this one, divide this. I don't know what to do yet. So let's leave that alone. If there's ever two sources of things, just leave it alone. Next, CO2. There is 1 mole of them on the product side. All right. So 1 mole on the product side. That's it, right? That's the only form of CO2, and it's in a gas, so we're good. So I guess we just write 2 as the way it is. We don't want to change this one at all. So CSGR plus O2 gas yields CO2 gas. And the enthalpy is unchanged. So it'll be delta HF equals negative 393.5 kilojoules per mole. Okay, so now we're good with CO2. Now water. There's 2 H2O gas in the products. H2O gas is only over here. So that means you multiply the entire equation by 2. Multiply it by 2 because that makes 2 of everything, and there's 2 waters there. 2 H2 gas plus 2 times 1/2 is 1 plus O2 gas yields 2 H2O gas. Then our delta HF, you guessed it, is also multiplied by 2. So negative 241.5 times 2 is negative 483 kilojoules per mole. So that's done. And before I continue, the answer, the question that we're being asked for here is, what is the enthalpy of formation in the top of reaction? What's the standard enthalpy in the top reaction? That's what's being asked for, just to clarify. So we're not just looking for this equation, we're looking for the enthalpy of this equation using this information of its intermediates. So that's the goal here. All right, so now we have all those. Now let's make sure everything is accounted for. And we'll use a different color. We use green. Okay, CH4. There's 1 CH4 here in the reactants. 1 CH4, we're good. We'll put that in a box. Here's what I like to do. I like to box them. 2 O2. There is 1 O2 in the reactants. 2 O2 in the reactants. Good. CO2. There's 1 in the products. 1 in the products. H2O. There's 2 in the products. 2 in the products. Key thing. Everything else should cancel out. Let's make sure that happens. We'll use blue. Graphite in the product, graphite in the reactant. Cancel. Cancel. H2 in the product, H2 in the reactant. Cancel. Everything's accounted for. Either canceled out or circled or squared. So now, to find our enthalpy of reaction, we know this math is right. We add them up. And our answer is 74.6 minus 393.5 minus 483. And we get negative 80 1.9 kilojoules. It wouldn't be kilojoules per mole anymore. Or it would be, I guess, kilojoules per mole of CH4, but we could just put kilojoules just to be more general. So that's what we get for our answer. And that would be the standard enthalpy of reaction of the top reaction in blue. Okay, is there any questions now? Anything? Hess's law is pretty fun. I like these questions because it's kind of, you got to be creative. You kind of like manipulate things. It's fun. Any questions? Okay, so here's the work. They kind of got this a little bit different. They got 10, I got 801.9. They got 802.5. What do they do? I don't know, but maybe they rounded different. Whatever. Oh, probably sig figs. No, same sig figs. I don't know. A little rounding thing. Whatever. Okay. So moving on, here's like the steps. And here is a different one. Where's this one? Here's another one. They kind of give it to you already, but basically, so if you're trying to find this reaction, the one in the green, and you have these two in black, you just go stepwise. So this one's, I think, pretty easy. You just add them, but let's just check if you just add them. We'll do the same thing. So NO, right? 2 NO in the reactant. 2 NO in the reactant. There's also 2 NO in the product. Wait a minute, I'm confused. Given the 2 reactions below, calculate for the one shown. Oh, for the one shown in red. What the hell is this doing there then? I'm confused with what this is asking for. Not sure what the green is. I'll get rid of the green. All right, let's do that one. So N2. So N2, there's 1 on the reactant side. Here's 1 on the reactant side. 2 O2. 1 here, 1 here. 2 NO2 on the product. 1 right here. And then the only thing you have left that is not accounted for is 2 NO, which is 1 here and 1 here, and they're both gone. So then you add all these up, you get this equation, and then you just add up the enthalpies, and you get 69 kilojoules, and that is your enthalpy of the reaction. So you have to manipulate. This is too basic, but you're going to have to manipulate the equations, and there may be 3 or even 4 equations, and you have to manipulate them to figure out the answer. So let's do this one as a more complex example. So we'll take it to a different page, or we'll copy it. All right, so given the following information, calculate the standard enthalpy for the following reaction. So we'll call these equations 1, 2, and 3, and then we'll call their modified products the prime. Call them prime. And we'll do this in black, and we'll cancel things out in red. Okay, so first look at the equation. 3 NO2. All right, find NO2. NO2 is here. There's 2 of them. NO2 is nowhere else. All right, and we need 3 of them. We have 2 of them. All right, so you can actually multiply equations by 1.5 and flip them at the same time. So we're going to do that because that's the only way to get NO2 on the left side. So we're going to multiply the equation. So we'll take 1 prime is going to equal, we're going to multiply it by negative 1.5 times 1. And the reason why we're multiplying it by negative 1.5 is because we have to flip it. And we need to multiply it by 1.5 to get this 2 to equal a 3. So our equation is going to be 3 NO2. I'm not going to write the gas stuff here. That's going to be equal to 3 NO plus 3 over 2 O2. And this is going to equal whatever, negative 173 times 1.5. And that's going to be our new delta H is going to equal 259.5 kilojoules. Okay. Does everybody understand what I did there to get to this equation? This one right here. I multiplied the top one by negative 1.5 to flip it to get the 3NO2 in the right place. All right. Next, move on to water. So water, we want one of them in the reactant. Here, you have 2 of them in the reactant. So we can divide by 2. So equation 2 prime is going to be equation 2 times 0.5. This is going to equal N2 plus 5 over 2 O2 plus H2O yields 2 HNO3. Hickel, Hibber, High, Hino. So there's a nitric acid. Delta H for there, we're dividing it by 2. So it's going to be negative 255 divided by 2, which is negative 127.5 kilojoules. Okay, everybody following me so far? So we got our H2 done, H2O. Next, our product side. Product side, 2 HNO3. Okay, let's look at our modified equation. So our HNO3 occurs in equation 2, but we already modified equation 2. That equation 2 has 2 HNO3 already in the products. So we're good there. Then the last thing in the products is NO. Let's look at the NOs we have. We have 3 NO in the products, no NO in the middle one, and then we have 2 NO in the products here. This is where this might be a little tricky. So our modified equation here has 3 NO. Our modified equation, or sorry, our original equation 3 has 2 NO in the product. To make this 1 NO in the product, if we flip this equation, we will have 2 NO in the reactant, 3 in the product. They will cancel out to have 1 in the product. So I'm going to write it down and then take questions. So 3 prime equals negative 1 times 3 because we're just flipping it. So it's going to be 2NO yields N2 plus O2 delta H enthalpy equals minus 181 kilojoules. Okay, is there any questions on what I did so far before we do the canceling?
Yeah, I have a question.
Yes, what's up?
Why did you skip water for equation 2?
I didn't. What do you mean? So for equation 2, we
Like you did equation 1 and then you went to equation 2, right? So
yes.
instead of going from NO2 to H2O, you went to NO2 to HNO3? Or am I just reading that wrong?
I think so. I went 1, 2, 3. I went through them. I didn't skip any of them.
Oh, okay.
So yeah. So I went through them in sequence. NO2 was obviously the first equation. H2O we modified the second equation, and then HNO3 we skipped HNO3 kind of because it was modified already in the second equation.
Okay.
So we didn't do anything after that.
Okay.
Okay, and then we went the third equation we modified to make NO in the right place.
Okay.
Okay, yeah, this stuff is tough to follow, so you'll have more time to learn it because it won't be on the exam. But okay, so let's go through let's box in green and then we will cross out in red. So 3 NO2 in the reactant side, 3 NO2 reactant side. Good. H2O reactant side. H2O reactant side. 2HNO3 product side. 2HNO3 product side. NO product side. 3NO and then 2NO. So then what happens is this cancels out, and you get 1NO. Just like algebra. Then everything else. The oxygens, that's where it gets complicated. So remember the first example, I did skip oxygen, and this one, you don't really mess with oxygen because sometimes there could be multiple sources. It's very common to have oxygen in equations. So for the product, you have 3/2, reactant 5/2, and then you have, this is 2/2. So 2/2 in the product plus 3/2 is 5/2. Those 5/2 cancel with the 5/2 here. So that's good. And then N2, you see reactant, product, done. Now we're going to add everything up, and we'll do it in blue. And our answer, I think they have the answer. The answer is going to be -49. So that looks like it could be 49. Let me double check. 259.5 minus 127.5 minus 181. Yep, -49. -49 kilojoules. All right, cool. So yeah, that's Hess's law. They won't get more complicated than that. The only thing there might be 4 equations, and also there's something they like to trick you with. Sometimes they put water. There's a liquid water and there's a gas water in the same problem. So you have to account for that. They're both different things. So you can't have a liquid water cancel out with a gas water. So you need to take, that's why I didn't write down the states here because I didn't have enough room, but it's important to write down the states and view each entity in its state, each compound in its state as an individual particle. So you need to cancel out the exact same thing with the exact same thing. Just because one's aqueous and one's a gas doesn't mean you can cancel them out. So they have to be exact same state. Okay, so are there any other questions on Hess's law? All right, if not, we will continue. There's another one you can try on your, oh, so this one's different. So we should go over this type also. Calorimetry we kind of did already, but this is the last thing. So I don't like the way these slides were. I guess I'm being lazy, but so Hess's law we're pretty good at that. But before I talked about Hess's law, I said something about products minus reactants, and we didn't really do any examples of that. So what I'm going to do is I'm going to put this example before Hess's law for future classes. So yeah, I'll put it right there. Oh no, what'd I do? Did I get rid of the slide? There we go. So there's a slide. Copy. Paste. All right. So we went over that the standard enthalpy for reactions can be written as the sum of the enthalpy of the products minus the enthalpy of the reactants. And that's what we can do here. So for this reaction, there's a lot of stuff written, but for this reaction, this one right here, the standard enthalpy is 180. Given that the enthalpy of formation for the silicon dioxide is this, the HF is that, and the H2O is that, calculate the enthalpy of formation of silicon tetrafluoride. We can use this equation to do that. So here's the way I would set it up. Well, first I'll get rid of this. We'll do it on the top. So here's how I would set it up. We would do the sum of the products minus the sum of the reactants equals your total reaction. So the reactants is, if we'll write the general equation, then we'll put the numbers in. So we'll do SiF4 is what we're looking for. So it'll be SiF4. It's going to be products plus 2 times H2O minus SI, the reactants, SiO2 plus 4 times HF equals 180. That's our equation. Does everybody understand what I did there? And we're using the molar ratios. Those would be our coefficients. Because if we have the enthalpy of formation of HF, but in the equation we have four of them, then we need to account for that. No questions? All right, then we'll finish it up. So SIF is what we're looking for, SIF4. So we leave that, SIF4 plus 2 times water. So water is negative 286 minus SiO2, which is minus 910.9 plus 4 times HF, negative 272.5 equals 180. And then you can solve for that. You solve for SIF. You can add all these up, do the math, do the stuff, algebra it out, and you get something. I don't know what you get, but let's do it right now. All right, so I'm gonna do this part first. I'm gonna do that first. So, oh no. All right, we'll do negative 910.9 plus 4 times negative 272.5. And I get negative 2000, negative 2001. So minus negative 2001 equals 180. And then you have this part. So then it'll be 2 times 286. That's going to be, or negative 286. That's going to be, so we'll write it down here. So we have SIF4 minus 572. That's going to be minus a minus, so it's going to be plus 2001 equals 180. So then we can add 572 both sides to 180, and you get 752. Then you're going to subtract 2001, and you will end up with, for SIF4, you'll end up with negative 1249 kilojoules per mole. So there you go. Cool. Any questions on that? So you basically use the product, the sum of the products minus the sum of the reactants, and you can get your enthalpy change in the reaction. Okay. So is there any other questions on anything? The rest of the chapter is just calorimetry, which we just did. Basically, you're just doing Q equals MCAT. You have some practice examples, whatever. So yeah, if there's no other questions, I will split you into breakout rooms to do chapter 7. To do the chapter 7 basic homework. And then the regular homework will be due on Sunday. But most importantly, or actually try to get it done by tomorrow or before the test. It'll be good practice for you. And the practice exams will be online, or they are online. So I'll show you that right now. So new share. I'll share with you this. So now you should be able to see the Moodle screen. And where's the Moodle screen? There you go. So the Moodle screen, you see exam 2 answers, fall 2017. And then 2018, you have the answers and everything. And then here's a chapter 7 study guide. That is it chapter 7 or exam 2? What did I do? I don't know why I made this. Oh yeah. That's pretty cool. So yeah. A pat on the back to my former self for making this. I will, you don't see it right now, but I'll show it. So here's the chapter 7 study guide. So yeah, it pretty much covers everything. It's a YouTube video on Hess's law. Some examples in there, state functions, endothermic, exothermic. they're the different equations broken down. So yeah, I was pretty good with that. Cool. Good. Go me. But yeah, so definitely look at this, and then there is an exam 2 study guide somewhere. If not, I'll make it, and I'll make a video on it like today or tomorrow. When are you posting the? Okay, Julie Ellis, good question. Tonight, I'll do it. Yeah, tonight. Tonight might mean later afternoon, but like tonight. But I'm gonna say tonight the latest. I'll be like binge eating pretzels, and then I'll at like 2 a.m. I'll be like, maybe I should make that video. So it'll be up by tonight. I try to eat healthier snacks. But anyway, let's Oh, Mary Madeline question: how can you see the video on YouTube? Oh, on the I'll post. Oh, the review video I'm gonna post. It'll be on Moodle, just like everything else. It'll be in the unit in June 15, Chapter 7. It'll be there. And then, or actually no, it'll be in June 17, Exam 2. And the one on the Word document, you just click the link. So, all right. I will end the recording. I should have done that.